Determine the p-value. So determining the p-value is going to happen using two things. Either Excel is going to generate one for us, so we do have some Excel labs that you should go through at some point, or we're going to use tables to do it. Okay. It's really important that we understand what a p-value is. I hate to hear that we get through the entire semester and we're not really sure what a p-value is. Underneath the PowerPoints is a video where they try to put it in simpler terms for you, using an example of a dog getting into the garbage can. It's about halfway down the pages. There's a video on p-value and an explanation. Actually, that entire website that's below the PowerPoints is really good. Anyways, I'll try to give you an explanation as certainly as best I can, but I think the video does a really good job as well. Okay. Especially since you can't see what there's nothing for me to write for you, and since I'm not there in front of you. So just using, I'll start with the textbook version definition, which is what's on the slide. So a p-value is what we use to determine the result of our test. We use this to determine whether we're going to stick with the assumption or whether we're going to agree that the assumption is not correct. And how we do that is we look at the chances of getting the information that we did, getting the sample that we did. You had an assumed average of 20, let's say. You believe the average was 20. But then you went ahead and did your test statistic, and your test statistic had a mean of 18. Now, 18 doesn't seem like it's that far from 20, but you'd have to take into account, the context and everything to really make that kind of judgment. But the question becomes, for the p-value, is 18 low enough, far enough below 20 for us to be able to say, you know what, yeah, if I'm getting 18, that's pretty far below the assumed average. So the average probably isn't 20. Or is 18 not that far below 20, and you're thinking, well, no, I got 18, but that's not that different, and that could just be simply that I'm using a data set, and the next person coming along might get 21. So that's not a big deal. But that's the question, is how do we make that choice? Is it a big deal that it's a little bit different, or is it not? That's what p-value tries to do. It tries to give you a probability. I shouldn't say tries, it does. A p-value gives you the probability that the information you got out of your sample is either really unlikely, that the p-value, the chances that you got that information is really unlikely. And if it is really unlikely, then you start to think, well, either I just had really bad luck and I got information from my population that just was really, really unlikely, but the assumed information is still true, or you start to think, okay, well, if the chances that I would get this information are that low, the chances that I would get that information and the mean being 20 and the chances that I would get 18 is 0.2%, well, that's probably not random chance. It could be. There's a 0.2% chance that I got that at random, but that seems pretty unlikely. I think it seems more likely to say that the average is actually less than 20. Since it was so unlikely that I would get this number in the first place, the fact that I did tells me that the average probably wasn't 20. It was probably something lower than that, something closer to what I got, 18. So that's the idea behind a p-value, is it's trying to give you the chances that you get the statistical information that you did. And if it's really, really low, we start to think, well, my luck probably wasn't that bad. It's probably more likely that the average is lower than what I initially thought, or higher. Okay. So if you still think you would like some more explanation on p-value, and you really should have a good understanding of it, because that's what you'll use in your other courses later on, I really suggest looking at that website that I've posted, and I can try to find some more if needed, but do please make sure you have an understanding of what it means. right, well, assuming we do understand what the p-value means, how do we actually find it? Well, a p-value is just a probability, and you're going to find it by using a z-value or a t-value. Those are your test stats. And you look up the probability the same way as before. Okay? And what I mean by before is I mean the test that you just finished, the normal distribution, you were looking up probabilities. You know, left tail was fine, right tail was 1 minus, and two tail we had to do a little bit of a, you know, a little funny calculation. That's what I mean by same as before. That's why it's so important that we learn how to use those tables early on, because we're going to use them for the rest of the semester to determine p-value. So if you are doing a test of average, mean, you will use a t-table. If you're using a test for proportion, you're going to use a z-table. And the z-table is the one that you already know. This is the one that's going to be new to you. Right? So I'm going to show you a little bit about it here on the PowerPoint. I think it's in the next slide. But I will have another video a little bit lower where you're doing some practice problems, and I'll go over the t-table in more detail in there, where you can actually see, you know, see me with the document camera, see me working on the table. Okay. All right. Finding p-value using the z-table. So you know how to do this already. I want you to grab your z-table. You can pause if you need to go grab it. Grab your z-table, your normal table, the one that we were using previously with the two sides. You're going to find the p-value for a left tail test when z is negative 1.84. Okay, and remember, you do know how to do this. So remember, for left tail, you were fine. You would look up the z value and there would be no issue. So go ahead and look up z is negative 1.84, get your probability, and you should find a number there. Okay. So before we do the next one, I'll actually say what the p-value is. So go ahead and have a quick look at it. So negative 1.84, you should find your p-value is 0.0329. 0.0329. Okay. Now for right tail tests, so if you want to look up a p-value for a right tail test, that's no different than what you were doing before. Again, when you had areas that were shaded on the right, you would look up the value, but you would remember to do 1 minus. So if you look up 1.67, so grab your table and look up 1.67, you can pause if you need to, 1.67, so when I look up 1.67, I get 9525. And when I 1 minus that, I get 0.0475. So 0.475. And that's my p-value. That's what I'm looking for. A p-value is just a probability. So I'm looking for these numbers out of the tables because I know that's what's in those tables, probability. If you want to do a two-tail test, so the two-tail test is going to be a little different than what you might have done before, because we're looking for something slightly different now. So there's just a little bit of an instruction here to help you. If you're looking for a two-tail test, look up the test stat, and this is going to be your test stat right here. Okay. So for a two-tail test, look up the test stat. All right, and that's this number. It'll come from step 2. Step 2 is where you calculate the test stat. So look up the test stat you get. I would say always look up the negative version. So even though here I gave you positive 205, okay, so positive 205, look up negative 205. I don't exactly have something, obviously to show you on the board, so I'll try to show you as best I can. But if you remember, the normal distribution is symmetrical. So the probability of being in this corner is the same as being in this corner, right? Because the distribution is symmetrical, you're getting the same probability in both corners, one from the negative value over here as you would from the positive side. Okay, so you're going to get the same amount of area under the curve from the same value on the left and the right, one being positive, one being negative. And you can verify that if you do a quick look. If you look up 2.05 and then 1 minus and then negative 2.05, you're going to find the same information. So the fastest way to do a two-tail p-value search is to look up the test stat. Always just use the negative version, even if it comes out positive like this one here did. Always just look up the negative version. Look it up, and whatever you get, multiply by 2. And again, the reason we're multiplying by 2 has to do with this picture in the bottom right. Again, the area that you're seeing down here in the corners is exactly the same. So if I can figure out, this amount of area over here, once I multiply that area by 2, that's what will make both pieces. Because remember, that's what a two-tailed test is. It's doing less than and greater than at the same time. So if we multiply the p-value by 2, that's what will get us both less than and greater than. Okay. So if we actually try to do this one, 205, what I would do is I would look up negative 205. So if I look up negative 205, I get 0.0202. So that tells me the area in one corner, 0.0202, and then the p-value is 0.0404 because that's the entire probability of being in either of those two corners, either of those two extremes. Okay. So if you want to see something a little more concrete, once we do the practice problems below in the document camera, I'll actually have my, my screen up and the paper in front of me and my hand, writing on the table for you. So you might find it a little easier to follow there. But hopefully that makes sense. It's exactly the same way as you were doing before, but the two-tail is a little different. All right, and there the three answers are. But now they're covered in marker. All right, the new one. So the t-distribution is the new one to you. It's going to be the one you'll use if you're testing average. Z table, the one I was just talking about, similar to before, is going to be for using in proportion. So the t-distribution is the one that we use when we are testing average, and we use it when we're forced to use S instead of sigma because we don't have our sigma, which is pretty typical. It's not very often that you would say, yeah, I know the population standard deviation, but I don't know the population mean. Well, why would that be the case? How could you know the standard deviation and not the mean? So it's not very often that we would know that. So it's more likely that you have S and not sigma. Now, something we already know is the sampling distribution of X bar will then follow a non-normal standard deviation called student t. So what happens here is that we do the sample standard deviation of the averages. We don't exactly get a nice normal curve. You get something pretty close though. So if you look at the pictures down here, the pink curve is meant to be the normal curve, but the t distribution is the blue and the black. Okay. So even though they do look very similar, you might say it looks exactly like a normal curve, just kind of squished down, you're not entirely wrong. The thing though to understand about the t distribution is that it's not going to have the same probabilities as a normal curve because due to the fact that you're estimating sigma with S, you're getting essentially a little bit more error, a little bit more room for error. So what happens is that we end up with more probability in the tails than we do in the center. But the more you take a bigger sample, the bigger the sample you can take, the curve actually gets closer and closer to a normal curve. And you'll see that when we actually talk about the table a little bit. But the more you can get the sample closer and closer to something, sorry, let me repeat that. The bigger the sample you can get, the more you're going to find these probabilities look more like a normal curve. But it's okay, even if we, that's the thing, is we don't have to have something with a huge sample. The t-distribution does a good job of finding our p-values for us. And it's a table just like our normal table. So we can use it without any difficulty. We don't have to worry about sample size too much. But yeah, if you do want something, closer to a normal curve, you have to use a big sample size. So we're going to use the t-distribution to find p-values. This just says the figure to the right is a comparison of two t-distributions and the normal distribution. So you can see as sample size increases, the t-distribution approaches the normal. And that's the idea, is that the bigger the sample size, the more this distribution is going to get closer and closer to a normal curve. There is going to be something new. You haven't heard this yet. But in fact, all the distribution tables except the normal curve are going to require what's called degrees of freedom, DF. A degree of freedom is going to be a small little formula that's attached to each test statistic. So you're going to see with each test statistic comes DF, a degree of freedom. And that's what you use to look up your probabilities. The reason we have this degree of freedom is because the degree of freedom, which is typically based on sample size, is going to affect probability. Okay? That wasn't the case with the Z table, the normal curve, but it is the case with the distributions we're using here on out. Essentially, with all of them, because most of them have a element of the central limit theorem as their requirements, if you remember the central limit theorem, it was all about bigger sample sizes made for better approximation to the normal. And because all of these tests require normality, the bigger the sample size, the better. Okay? So we have to take sample size into account because that's going to tell us, where on these tables, which probabilities are going to best fit that curve. Because the bigger the sample size, the better the curve. So that's been taken into account with these distributions, is the fact that unless you have a large enough sample size, your probabilities are going to be different. And that's okay. The tables have taken all that into account. We just need to make sure that we use degree of freedom when we look up the tables. So the finding of the p-value using a t-table instead of the normal table. So the previous two slides ago had the Z table, and it had p-values very similar to what you're used to working with. It was, left is fine, right is 1 minus, and two tail, look up the negative, multiplied by 2. But the t-table, and again, similar to the other tables you're going to learn, is going to use a little bit of a different technique. Okay? And again, I can show you more detail when we actually do this on paper, but to give you an idea now, the first thing to make note of, like I said, is that you're going to see degrees of freedom here. Right? It's right here in the table. Right? This is just a snapshot of a part of the t-table. Okay? If you look at the printout you have of the t-table, this is just a small snapshot of that. The t-table uses degree of freedom. For now, for this week's lecture, the only time you need this is for the t-test, which is testing of mean. And for this particular test, it's not for all tests, but for this particular test, one sample mean test, the degree of freedom is n minus 1. So sample size minus 1. Okay. So the idea behind using these tables to determine your p-value. To find the p-value for a left tail test, when test statistic is the following. and sample size is 25. Now this is all information that you would have before you get to the point of a p-value. You would know if you're doing left tail, right tail, or 2, because that would be in your hypothesis. You would have your test statistic calculated. Okay? That would be step 2. You would have that t-value already figured out. And you would already know your sample size, because that would be part of your information from the very beginning. Okay? It's now that you're in step 3, determining p-value, you would use this information in particular to help you get the answer for the p-value. So here's how a p-value works. Figure out your degree of freedom. In this case, it is 24. N minus 1, 25 minus 1, 24. Okay? Now here's the difference, and this is why this one is different. Some people find it actually easier than the other table, but I guess to each their own. So this is how this one is different when it comes to looking up p-values. Here's your goal. Forget about the sign. Don't worry about if it's positive or negative. What you're going to do is look for in the list, and you can only be in this list here. You can only be in the row for 24. Okay? You can't be anywhere else. You have to stay in the row for 24 because that's your degree of freedom. So these are the only ones you get to choose from. Okay, above that yellow line there. So what I'm going to look for in that row beside 24 is I'm going to look for where 1.45 would be. And I want to be somewhere in between. Where would be a number? Where would 1.45 fall? Well, this is too small. First one's too small. Next one's too small. 1.3 is pretty close. 1.48. Okay, that's too big. So 1.45 should fall right there where my little mark has been made. It should be somewhere right in between there. So my p-value, so then I'm going to go up, and there's two rows, one tail and 2. Now obviously 2 tail is for a 2-tail test. 1 tail area is for a left and a right tail test. So you'll use a 1 tail test area if you're doing left or right. So I'm going to move up, and my p-value is going to be right here. All right, because 1.45. So here's why I have 2 numbers and not 1, because you're used to using the z value and you get 1 number. 1.45 is somewhere in between these 2 numbers, 1.318, 1.487. Problem is, I'm not going to try and figure out exactly how far away they are or which one is closer. We can't do that. We need to actually use in between. So because 1.45 is somewhere in between, what I can say is that the p-value must be somewhere. The p-value has to be somewhere. The probability of being 1.45 has to be somewhere between 0.075 and 0.1. So 7.5% and 10%. The chances of me getting 1.45 is somewhere between 7.5% and 10%. That's what I now know. Okay? There it is there. Okay, so that's what we do, is we don't actually get a number, we get a range, and that's the best we can do unless we're using a software. We're not going to get an exact value, we're going to get a range, and that's perfectly fine. That's actually all we need, because we're going to see how we make our conclusions afterwards, but the fact that it's a range is perfectly fine. We can still make our conclusion with that. All right, before I do the next one, I just want to tell you a few more small things. For example, what happens if you're, if you have a number like 0.5, let's say. So let's say your test statistic was 0.5 and you were over here. What would that mean? Well, that would mean if you had 0.5 and you were here, so if you were 0.5 and you were here, when you go up, and let's say it was a 1-tail area, so when you go up to the top here, you would say, well, if you look at the numbers, what's happening? They start off very small on the right and they get bigger and bigger. So if you had a test statistic of 0.5, you would say the p-value is greater than 25% or 0.25. Okay, because you can see the numbers are getting bigger as you go left. So greater than 0.25. The opposite would be true if you were down here. So if on any of the examples you kind of fall off the edge, the number that you're looking for is very large. So let's say I had a test statistic here equal to 4, and I get to the end of the row and I say, well, it's past the very last number. Well, that's fine. So what that means for your p-value when you go straight up is that, as you can see, it's getting smaller and smaller as you move right. You would say the p-value is less than this 0.0005. Okay, that's what we would do. Okay, so if you fall off the chart, you can just say it's greater or less than the maximum minimum values. Okay. All right, let's try this last one. So I have a degree of freedom of 29. The reason it's 29 is I got to do n minus 1. Okay, don't forget to do n minus 1. So I'm looking at the row for 29. It's a two-tailed test, I'll keep that in mind, and I'm looking for the number 2.39. So where do I find in the row the numbers that are between, the 2.39 is in between? So I move to the right, and I find right here. So 2.39 is somewhere in the middle there. And as I go from 2.39 in between here, as I move up, straight up, I stop at, this time I'm going to stop at the two-tail area. So I'm going to stop right there. And I'm going to say, okay, well, if 2.39 is in between those two digits, the p-value must be somewhere in between those two, 0.02 and 0.05. And there it is there.